We'll now try to analyze the data which is a little bit more challenging to fit. Let's take a look at the YSC data that is available for download once again. We can see here that we have the relaxation on modulus. Let's take a look at this data using the Averly-Aknegami analysis window. As we see here on the modulus, it appears to be only one relaxation. However, we should always inspect the relaxation or the data in more than one formalism. This is a clear example of how this can be useful, because we see that really from the real part of the permittivity we have more than one relaxation. Let's analyze a little bit lower temperatures. Let's try to fit this temperature value. We will start by giving the starting conditions, and we'll take these values from the permittivity values here. So this is the static value, the infinite 1, time constant should be around here, and then the infinite of the second relaxation, infinite permittivity. We can now change back to the modulus, and we'll take the time constant value of the second relaxation here. Let's try to fit this using the fit to peaks. It doesn't appear to be that good. Let's try a different algorithm. It's also not that good. So let's go back to the permittivity and let's restrict a little bit more our starting conditions. So let's say that the infinite permittivity value is around here. So in this lower part we can give a lower and upper bound for our variables to fit. So in this case I'll say that this value should be between here, above this, and below this one. Let's try to fit now in the permittivity. Okay, let's also say that the alpha and beta parameters should not be very low, so at least they should be above 0.3. Let's do the same. Let's make here. Now let's go back to the modulus and see if we have a better result. Also not that very good. Let's increase this parameter, 0.4, 0.4. Here should be 0, and here 0.4, and here 4. Okay, this seems to start to be a little bit more reasonable. Let's see if this fit result makes sense to our permittivity data. So we will load these fit results. Let's try once more. Okay, this seems better. Let's now fix these values, and let's go back to the permittivity and see if this solution is also good to fit the permittivity. So this is a good example on how or why we should really always see more than one formalism, because the modulus is fitting very nicely but the permittivity is not. So let's reset these limits Let's go back to this value. This one is more or less. Let's restrict this one and this one again. Let's try this algorithm. Again, putting this here. Let's increase a little bit the fitting power. Okay, this seems to be a little bit closer. Let's load these fit results, go back to the modulus and see if this is a good starting condition for our data. Change the algorithm again, and with this one we're getting a nice fit. Let's see if we can improve a little bit. Let's fix the values, go back to permittivity once again, and it's pretty close, I would say. Maybe the static value should be a little bit higher, so we'll put this again to the default value. Maybe resets once again. Loads. And I would say this one is pretty much the best we can do. Let's check the residuals. They are very good, below 5%. So let's loads and fix once again. Go back to the modulus and see if this result is good for the two formalisms. And it is very good. Plot residuals once again very low. So I would say that for now this fit seems to be the real solution for this data. So we have two relaxation and the DC conductivity. So we can also use the impedance data and the equivalent circuits to double check if this fitting parameters are good. So let's take a look now at this equivalent circuit model analysis window. Let's analyze the same temperature, so 541. Let's plot the normalized impedance, and let's just make a very quick fit to see the total resistance of the electrolyte, so we can choose the fit circle option. Let's give between this point and around here. Let's see if it makes good fit. Yeah, it's good. So it is telling us that the total resistance should be this value here. Let's calculate the conductivity using the total resistance of the electrolyte. So it will be 1 divided by 8.55675. So this gives us 1.17. Let's now confirm to our value. So this one is on Siemens per meter, while this one, when we plot the normalize, it's on Siemens. It's on ohm. The impedance, it's on ohm per centimeter. So the conductivity that we are calculating here manually it's really on ohms per centimeter. So if we put this on ohms per meter to have the same as here, we'll have 1.16 to the power of minus 4, which is the same that we have here. We can also use this window to perform equivalent circuit model analysis, and let's once again analyze the same data, the same temperature, and now let's go back to the regular temperature. So we'll make plots, and now we see that we have two semicircles, one very larger one with a large resistance, and the lower one here at lower frequencies. So this should be very well fitted using these equivalent circuits. Let's try to use this one. So we need to first enter the first parameters for the RCPE and then to the second RCPE term. So first let's define the resistance of the first semicircle. So we can again use this button and give 2 mouse clicks. This will calculate the resistance between these 2 points. I'm expecting this to be the bulk resistance or the bulk contribution, and this lower semicircle should be the grain boundary response. So let's say this should be 1 minus 11. The power law we can give 0.8 as starting conditions. And now let's go back here and let's try to calculate the resistance around here. And assuming this should be grain boundary, let's give something like this for starting conditions. We can select several algorithms for fitting, and also we can choose one of these 3 weighting methods. Let's start using this one for starters. So let's fit the data. It's pretty close actually from I would say the best fits already. Let's check the residuals. Yeah, they are very low. Only at higher frequencies we have some dispersion on the real data, the real part of the impedance. But let's try to load the fit results and run one more time to see if we can get slightly better fits. It's pretty much the same, so I would say this is the best fit we can get, which is very good already. And we can see the resistance of the bulk, and we can also see the resistance of the second semicircle, which should be the grain boundary, and we can see the capacitance values are close to what should be the bulk and the grain boundary response.